So, in the last lecture we started the Mellin transform. We have seen the definition, how to find out the Mellin transform of a function, how to find out the inverse Mellin transform of a function, and also the basic definition and some applications, some examples we have done. In this particular lecture, what we are going to do is to study certain properties of Mellin transform. The first property is, we call it as the scaling property, that is, if the Mellin transform of f x equals a capital F bar s, then the Mellin transform of f of a x, this is equals to the a to the power minus s into f bar s. If you see this thing, scaling property also we have done for the case of Laplace transform, for the case of Fourier transform, this thing. So, please note that if Mellin transform of f x is capital F bar s, then Mellin transform of f of a x will be a power minus s into capital F bar s. Let us see the proof of this. Let us start with this thing, Mellin transform of f of a x. This is equals, from definition you can write down 0 to infinity x to the power s minus 1 into f of a x dx. So, if I put here now a x equals v on this, a x equals v. So, the limit will remain same. For x equals 0, v is 0, for x equals infinity, your v is infinity. So, a x to the power s minus 1, which will be v to the power s minus 1 by a to the power s minus 1 into f of v into dv 1 by a into dv. This equals, you can write down, this is 1 by a to the power s 0 to infinity v to the power s minus 1 into f v dv, and this integral is nothing but a power minus s. So, let me write down equals a power minus s into, this is nothing but the Mellin transform of the function f b. So, that you can write down this is nothing but f bar into s. So, this completes the proof that Mellin transform of f of a x is equals to, it is nothing but a to the power minus s into capital F bar s, that is a to the power minus s into Mellin transform of f of x. So, the proof was quite simpler. This was the scaling property, that Mellin transform of f of a x, this equals 0 to infinity x to the power s minus 1 f of a x dx. You are put substituting a x equals v, so that you will obtain 0 to infinity v to the power s minus 1 a to the power s minus 1 f v into dv by a. This I can write down 1 by a to the power s 0 to infinity v to the power s minus 1 into f v dv. So, this integral is nothing but the Mellin transform of f x. So, that I can write it as a to the power minus s into f bar s. The next property we call it as the shifting property, that is your Mellin transform of x to the power a f x, that is whenever you are shifting it x to the power on x direction, x to the power a f x equals capital F bar s plus a. Let us see the proof of this thing. Let us start with Mellin transform of x to the power a into f x. From definition, this is equals to nothing but 0 to infinity x to the power s minus 1 x to the power a into f x dx. So, this equals, you can write down 0 to infinity x to the power s plus a minus 1. If I combine these both powers of a, then into f x dx. And this clearly is nothing but the Mellin transform of the function of s plus a, that is Mellin transform of f of x plus a. So, this equals, I can write down f bar s plus a. So, because this is nothing but the Mellin transform of f of x plus a, and which I can write down f bar s plus a. Therefore, Mellin transform of x to the power a f x, this is equals to f bar s plus a. So, this completes the proof of the first one, that Mellin transform of x to the power a f x equals f bar s plus a. The next property is Mellin transform of f of x to the power a, this is equals to 1 by a f bar s by a. Please note this one. Mellin transform of f of x to the power a, this is equals to 1 by a f bar s by a. To get the proof of this, let us start with Mellin transform of f of x to the power a. This is equals to 0 to infinity x to the power s minus 1 into function of x to the power a dx. Let us substitute x to the power a equals b. If I take x to the power a equals b, means x equals b to the power 1 by a, and your dx will be equals to x to the power a. So, 1 by a v to the power 1 by a minus 1 into dv, x to the power a minus 1. So, that I am making as v to the power 1 by a minus 1. So, if I substitute it here, this is nothing but 0 to infinity v to the power x to the power s minus 1. So, it will become v to the power s minus 1 by a into f of x to the power is v into 1 by a v to the power 1 by a minus 1 into dv. This equals 1 by a can come outside, 0 to infinity. This v to the power I can combine together. If I combine together, then s plus s minus 1 plus 1, and this will be minus a, basically s minus 1 plus 1 minus a whole divided by a. This v power I am combining together into f of v into dv. So, this equals, after simplification, this becomes v to the power s minus a by a, which you can write down s by a minus 1 into f of v dv. And now you see this integral, that 0 to infinity v to the power s minus a minus 1 into f v dv. This is nothing but from the definition of the Mellin transform, the Mellin transform of the function f of x by a. So, that this equals, you can write down, this equals 1 by f bar s by a. And this completes the proof of this, that Mellin transform of f of x by a, Mellin transform of function of x to the power a, this is nothing but 1 by a f bar s by a. Next one is, the third one is Mellin transform of 1 by x function of 1 by x, this is equals to f bar 1 minus x. Mellin transform of 1 by x, f of 1 by x equals f bar 1 minus s. The proof of, for proof of this one, we can start with Mellin transform of 1 by x function of 1 by x. This is equals to, from the definition again, 0 to infinity x to the power s minus 1 1 by x into function of 1 by x dx. Now, again you substitute 1 by x equals v, so that your x equals 1 by v, so that you can write down your dx is minus 1 by v square into dv, and the limit of the integral just I am showing for x 0 and infinity. For x equals 0, your v is infinity, and for x equals infinity, your v is equals to 0. So, therefore, limit of the integration will be from infinity to 0, v is moving from infinity to 0. So, this equals, you can write down infinity to 0, v to the power 1 minus s into v into f v into dx is minus 1 by v square into dv. So, your 1 v will be cancelled. So, v 1 v here also will be cancelled. This minus will come outside, minus infinity to 0, v to the power minus s into f v dv. And this equals, you can write down this minus, you can interchange, will go out. If I make 0 to infinity, v to the power minus s, I can write down 1 minus s minus 1 into f v dv. Again, this is nothing but the Mellin transform of the function 1 minus x. Mellin transform of the function 1 minus x. So, that this equals, I can write down f bar, this is nothing but the f bar 1 minus s. So, therefore, Mellin transform of 1 by x, f of 1 by x, this equals the Mellin transform of 1 minus s. So, this completes the proof that Mellin transform of 1 by x, f of 1 by x equals the capital F bar 1 minus x. The next one is Mellin transform of log of x into f x equals dds of capital F bar s. So, the function, if I multiply with log x, then it is basically becoming the dds of f bar s. To see the proof of this one, again we start from the left hand side, that is Mellin transform of log of x into f x. This is equals, from definition, you can write it as 0 to infinity x to the power s minus 1 into log x into f x dx. Once I am writing this from definition, Mellin transform of log x f x equals 0 to infinity x to the power s minus 1 log x into f x dx. And also I know this thing, capital F bar s, from the definition of Mellin transform, it is nothing but 0 to infinity x to the power s minus 1 into f x dx. This I know. Mellin transform of 0 to infinity x to the power s minus 1 f x dx equals capital F bar s. Now, if I differentiate with respect to s on both sides, that is dds of f bar s, this is equals to 0 to infinity dds of, simply it will be x to the power s minus 1 into f x dx. Now, please note this thing, that ddx of a to the power x is equals to log a into a to the power x. We know this thing, that ddx of a to the power x equals log a into a to the power x. For this problem, basically here now, if I interchange, your a is x and your x is s minus 1. If I use this formula over here, where your a is x and x is s minus 1, if I use this one here, this equals, you can write down 0 to infinity x to the power s minus 1 into log x into f x dx. Please note that I am getting this using this differentiation, that ddx of a to the power x equals log a into a to the power x, and for this integral dds of x to the power s minus 1, a will be x and x will be s minus 1. And if you see this thing, 0 to infinity x to the power s minus 1 into log x f x dx, this is nothing but, from the definition of Mellin transform, we can write down, this is equals to Mellin transform of log x into f x. And this completes the proof that Mellin transform of log x f x, this is nothing but equals to dds of f bar s. So, this completes the proof of the last one, that Mellin transform of log of x f x equals dds of f bar s. The next property is on the Mellin transform of derivatives. We know the Mellin transform of f x is capital F bar s. Now, we are saying that Mellin transform of f dash x equals minus s minus 1 f bar s minus 1, provided x to the power s minus 1 f x vanishes, that is approaches 0 whenever x approaches 0 and x approaches infinity. So, we are saying Mellin transform of f dash x equals minus s minus 1 f bar s minus 1, provided x to the power s minus 1 f x vanishes as x approaches 0 and x approaches infinity. So, to prove this thing, we are starting with the left hand side, that is Mellin transform of f dash x. This is equals from definition 0 to infinity x to the power s minus 1 into the function which is f dash x. This is equals to 0 to infinity x to the power s minus 1 f dash x dx. Now, if I use integration by parts, this will be x to the power s minus 1 into f x 0 to infinity minus the derivative s minus 1 will come 0 to infinity x to the power s minus 2 into f x dx. Now, this equals, I am keeping it as it is at present, x to the power s minus 1 f x 0 to infinity minus s minus 1 into 0 to infinity x to the power s minus 1, that is x to the power minus 1 f x into dx. Now, if you recall that x to the power s minus 1 into f x, this approaches 0 whenever x approaches 0 or f x approaches infinity, because in the definition itself we told that provided x to the power s minus 1 f x approaches 0 or whenever x approaches 0 or x approaches infinity. So, this particular term will vanish, this term will vanish due to this condition. So, that this equals, simply you can write down s minus 1 0 to infinity x to the power s minus 1 into x power minus x into f x dx, and this if you see, this is nothing but minus s minus 1 into f bar s minus 1, that this is from the definition x to the power s minus 1 x to the power minus x dx, which is nothing but f bar s minus 1. So, therefore, what you are getting, this is equals to Mellin transform of f dash x equals minus s minus 1 into f bar s. What was the this thing, that Mellin transform of f dash x equals minus s minus 1 f bar s minus 1, provided this x to the power s minus 1 f x vanishes as x approaches 0 and x approaches infinity. This we have shown that why we have to take this assumption. We started with the left hand side, we are just using the by parts. Now, this first term actually will vanish, and because of the given condition, and second term is nothing but the s minus 1 minus s minus 1 into f bar s minus 1. So, in the same way we can show that Mellin transform of f double dash x, this is nothing but s minus 1 s minus 2 into f bar s minus 2. So, minus plus will come together. So, Mellin transform of f double dash x equals to s minus 1 s minus 2 into f bar s minus 2. In general, if I have to write down, in general, then we can write down Mellin transform of f n x. This is equals to minus 1 whole to the power n This will be equals to, actually in terms of gamma function, you can write down gamma s by gamma s minus n into f bar s minus n. This I am writing directly, I have not given the proof, or this again you can write down minus 1 to the power n gamma s minus n into Mellin transform of f x, where the variable is s minus n, not s. This by this way also you can write down, provided one more condition I have to use. Provided what happens? Your x to the power s minus r minus 1 into f r x approaches 0 as x approaches 0 and infinity for r equals 0, 1, 2 up to n minus 1. So, the Mellin transform of f n x is equals to this thing, minus 1 to the power n gamma s by gamma s minus n into Mellin transform of f x, where s minus n I have written means the variable for s will be replaced by s minus n. So, for the next step, here Mellin transform of f double dash x was f dash x was minus s minus 1 into f bar s minus 1. So, it will be equals to s minus 1 s minus 2 into f bar s minus 2. In general, I can write down Mellin transform of f n x equals minus 1 to the power n gamma s by gamma s minus n. I am writing that way, f bar s minus n, and this I can write down Mellin function of f x s minus n, where this value approaches 0 for r equals 0, 1, 2, n minus 1. The next property is if Mellin transform of f bar f x equals capital F bar s, then Mellin transform of x f dash x equals minus s f bar s, provided your x to the power s f x approaches 0 as x approaches 0 and infinity. Let us see the proof of this one. We are starting with Mellin transform of x f dash x. Mellin transform of x f dash x equals x to the power s into, actually x to the power s minus 1 into x f dash x dx. So, that this you can write down 0 to infinity x to the power s into f dash x dx. So, if I use the by parts, this is x to the power x f x 0 to infinity minus s into 0 to infinity x to the power s minus 1 into f x dx. Value of this integral is equals to 0, because x to the power s, it is given provided x to the power x s f x approaches 0 whenever x approaches 0 or infinity, and this integral is nothing but capital F bar s, that is Mellin transform of f x. So, that this is equals to minus s into f bar s. Similarly, I can write down Mellin transform of x square f dash x. This is equals minus 1 whole square s into, I can prove this thing, s into s plus 1 into f bar s, and in general if I have to write, I can write down Mellin transform of x to the power n f dash x. This is equals to minus 1 to the power n gamma function, I can write this thing gamma s plus n by gamma s into, this is nothing but again capital F bar x. So, Mellin transform of this x to the power n f dash x, in general you can write down minus 1 to the power n gamma s plus n by gamma s into f bar s. So, from here you can tell that I have to prove this Mellin transform of x f dash x equals to minus s f dash x. So, I am starting with this using integration by part. The first limiting value, first term will vanish, since x to the power s f x approaches 0 whenever x approaches 0 or infinity, and second integral is nothing but capital F bar s. So, this completes the proof of this. Similarly, I can show that Mellin transform of x square f dash x equals minus 1 to the power whole square s plus 1 into f bar s. From here, in general, I can write down Mellin transform of x to the power n f n x equals minus 1 to the power n gamma s plus n by gamma s into f bar s. So, in general, we can tell this thing. Next one is Mellin transform of differential operator. If Mellin transform of f x is f bar s, then Mellin transform of x d dx whole square of f x, this equals to Mellin transform of x square f double dash x plus x f dash x. So, if this one minus 1 this is the differential operator. So, x double dash x equals this, and this equals, we can write it as minus 1 whole square s square f bar s, because x d dx whole square I am writing in this particular form. So, for the proof, your x d dx whole square of f x, this you can write down x into d dx of x f dash x. I am putting it inside, so that whole square was there. So, this equals x into x f double dash x plus f dash x, and this is nothing but x f dash x plus x square f double dash x. So, actually whatever I shown, that Mellin transform of this equal to this Mellin transform of this part we have shown over here. So, this is fine. From here now I am starting that Mellin transform of x d dx whole square of f x, this is equals to, we have just now shown Mellin transform of x square f double dash x plus x f dash x. I can break it so that I can write down Mellin transform of x square f double dash x plus Mellin transform of x f dash x. Now, by 7 property 7, whatever we have used, from property 7, if I substitute the values, I will obtain this as minus s f bar s plus s into s plus 1 into f bar s. So, this equals, you can write down minus 1 whole square into s square into f bar s. So, this completes the proof that Mellin transform of x d dx whole square of f x equals minus 1 whole square s square into f bar s. In general, again in the same way, if you proceed, then you can write down x d dx whole to the power n of f x. This is equals to minus 1 whole to the power n s to the power n into f bar s. This I can prove this thing. So, therefore, if you see this one Mellin transform of x d dx whole to the power n f x, this equals minus 1 to the power n s to the power n f bar s. So, that just see here I had to prove this thing. So, I am starting with this x d dx whole square of f x, this we can write down x into d dx of x f dash x. So, that you will get the same thing, and this if I break x into x f double dash x plus f dash x. So, that this value is equals to x f dash x plus x square f double dash x. So, Mellin transform of this equals Mellin transform of x square f double dash x plus x f dash x, and this equals Mellin transform of x square f double dash x plus Mellin transform of x f dash x. This is by property 7, I can write it as minus s capital F bar s plus s into s plus 1 into f bar s. So, if you simplify it, it will become minus 1 whole square s square into f bar s. So, in general, if you have to say, you can tell that Mellin transform of x ddx whole to the power n f x, this equals minus 1 to the power n s to the power n f bar s. So, in general, I can tell this thing. So, in the next lecture, what we will do? We will see the Mellin transform of integration of a function and the convolution of the Mellin transform of two functions, as well as some applications of Mellin transform.